Unified dynamics. Distinction theory.
For over a century, the greatest mathematical triumphs in physics have relied on an untested assumption that space and time exist as a continuous background. We treat the universe as a pre-existing canvas where physics happens. Treating space as a given container has a specific cost. To make the equations of the Standard Model and general relativity match our observations, physicists must manually insert free parameters, numbers tuned by hand because the theories cannot predict them on their own. We have to ask what happens if space and time are not a canvas at all, but structures that must be mathematically generated. Unified dynamics, or UD, treats reality as a self-building system. It replaces the background assumption with a single recursive geometric rule. In this framework, particles, matter, and gravity emerge as byproducts of relational information transport. They are the secondary results of how data moves between locations. Removing the continuous background eliminates the need for free parameters. By defining how structure is built, we can derive the constants of the universe strictly from the mathematical cost of that construction. The foundational layer of the UD model is the substrate. This is an abstract web of connections, a relational network that precedes the existence of space. Each location in this substrate is a locus, containing three values: a burden measuring unresolved load, an orientation defining direction, and a closure branch detailing its path. Stability requires that geometric relations obey the closure law. They must loop back and connect to themselves. Structure begins when a point expands into a line, branching and closing to form a flat triangle. Reaching saturation, the system escapes into a new dimension, extruding upward to form a pyramid. Finally, it closes its base, locking into a rigid tetrahedral solid. This tetrahedron acts as a stable carrier. It is the minimal three-dimensional structure capable of remembering its state and relaying information to its neighbors. Three-dimensional space exists as the first geometrically locked configuration that allows information to persist without collapsing. Information propagates by stepping through this lattice of locked tetrahedrons. When a signal successfully returns to its starting state, the system remains flat. This perfect return is the condition for uncurved space. However, localized routing rules often conflict. When a signal is forced into a detour, the loop fails to close cleanly. This creates a gap between the start and end point, a transport mismatch. Spacetime curvature is the measurement of these accumulated routing failures across the network. Because the network must resolve its internal load, these mismatches cannot be discarded. The inconsistency is frozen into the lattice, creating a persistent topological defect. Matter is the physical manifestation of these frozen defects. The topology of the loop determines the type of particle created. A defect requiring 2 full turns to clear a sign flip becomes a fermion precursor, the basis for electrons. A 1-turn clean closure becomes a boson precursor, like a photon. Mass, spin, and charge are the mathematical consequences of how a specific information loop failed to close. As the structural complexity of the network increases, the system encounters a mathematical threshold. At the n=7 partition scale, purely computational fields can no longer stabilize into closed packets. The information becomes too dense to lock. We can track this instability in the standard Hamiltonian equations. Without an external influence, the violation terms act as a repulsive force, pushing the information apart. This phase space graph shows a monotone energy landscape. There are no stable wells where information can cluster, so it remains a diffuse dust. Stabilizing the system requires the injection of the Einstein coupling. This value is derived by normalizing the full three-dimensional angular support of a local cell. This coupling introduces simplicial gravity, a geometric attraction that pulls the nodes of the lattice together. Look at the updated Hamiltonian. As the gravitational term is applied, an inflection point appears exactly at the 88.4 mark. This deep potential well provides the clamping force necessary to pull computational states together. The probability that a packet will close and lock jumps from 34% to 92%. Gravity functions as the temporal glue of the network. It is the mathematical condition that allows complex information to hold together rather than dissolving. For unified dynamics to function as a physical theory, it must produce quantitative values that match our universe. Every transport step across the lattice is governed by three distinct geometric gates: a primary partition of 1/2, a branch fraction of 7/16, and a final 1/6 coherent slot. Multiplying these three constraints defines the irreducible mathematical toll the substrate extracts from every signal, exactly 7/192. This specific ratio allows us to derive the bare fine structure constant and the Koide ratio for lepton masses without using any tuned parameters. This ratio also predicts the bare spectral index of the cosmic microwave background. By subtracting the 7/192 attenuation from the system's baseline, we get a value of 0.965, the exact measurement of the lumpiness of the early universe. To test this geometry, the GAP5 simulations tracked 38 cluster centroids as they formed on a two-dimensional lattice. Measuring these clusters requires correcting for the dimensionality mismatch. A two-dimensional slice of a three-dimensional fractal must have its measured dimension increased by exactly 1. The simulation results confirmed the 7/192 derivation. The clusters formed an attractor with a Hausdorff dimension of 2.965, matching the observed CMB spectral index. These results indicate that a zero-parameter geometric grammar dictates the measurable constants of our universe. A physical theory is only valid if it defines the conditions for its own falsification. We can test UD against general relativity by observing the gravitational waves captured by the LIGO observatories during black hole mergers. General relativity predicts every massive collapse follows a uniform process, resulting in a standard event horizon. Unified dynamics identifies a second possibility, a rupture-first collapse. This occurs if the structural density of an object exceeds the transport network's carrying capacity before an event horizon forms. This difference would be visible in the gravitational waveforms. While Einstein's theory predicts a smooth wave, UD predicts that the signal will drift out of phase and peak with a sharp amplitude burst at the moment of merger. This burst, alongside a complex multi-mode ringdown, is a signature general relativity cannot account for. The presence of these signals would demonstrate that physical laws are the emergent geometric limits of information fighting to exist.